Okay, it's possible that you are wondering why in section 16.1 we introduced vector fields with great excitement, only to abandon them to start talking about line integrals in section 16.2. Well, the reason is that one of our prime examples of a line integral is going to involve a vector field. So I'm going to have F be a continuous force field. So that just means each of the component functions of F are continuous. And this could be in 2 space or in 3 space. And I'm going to have C be a piecewise smooth curve. Curve. And C is going to be passing through this force field. So maybe C goes something like so. Okay. But it's passing through this force field. So what that means is that at every point on C, there's some force. Now there are forces where C isn't as well, but there are going to be forces at each one of these points on C. And it's possible that some of those forces are sort of compatible with the orientation of C, so would be sort of helping to push something along that path. Some of those forces might be sort of pushing backwards. Okay. But what we're going to do is we're going to take a look at a particle that's moving along C and see the work that's done by the force field acting on that particle. Now, super important to recognize, the particle is not moving along the path because of the force field. The particle is moving along the path because the particle is moving along the path. The force field is doing work that either helps or hurts. Great example, I love to ride my bike. Sometimes when I'm riding my bike, the wind is blowing. So I am going through a force field because the wind is exerting a force on me. Now, when the wind is at my back so that it's pushing me along, I am very happy. When the wind is blowing against me, I am very grumpy and unhappy and irritated at the world. Okay, because then that force field is actually doing what we would call negative work. So positive work will be when the force field is helping to push the particle along. Negative work would be when the particle is pushing when the force field is pushing the particle back. And we're going to try to calculate the net amount of work that the force field does on a particle moving along this curve. Okay. So, we're going to have the dilemma that, as you can see, the direction of the force isn't necessarily always going to be quite in line with the direction of the curve. So let's just recall from way back when we first started working with vectors, that if I have a force vector, and if that's going to move me from point P to point Q, so that my displacement vector is the vector PQ, we had learned how to calculate the work done by this force in moving the particle from P to Q. The work was F dotted with PQ. So we replaced the idea of multiplying a constant force by the distance that the force moves an object if it's moving in the direction of the force, with dotting the force with the displacement vector. If you remember, where that came from is we could break this force up into components. This right here would be the projection of the force onto PQ, and that would be the component of the force that's actually doing the work. And so then I would be able to say, okay, so the magnitude of the force is going to be the magnitude of just this component, and then the distance is going to be the magnitude of PQ. But if we take a look at this dot product, that's actually the magnitude of F times the magnitude of PQ times cosine of theta, where theta would be the angle between the force and the displacement vector. Okay. So F and cosine theta, just using right triangle trigonometry, gives me the magnitude of this component of force, and then the magnitude of PQ is the distance. Now, when we saw this before, we pretty much were working with theta being an acute angle. Now we're allowing for the possibility that theta is obtuse. The formula still holds, but of course, because cosine of theta would be negative, that just means we're getting some negative work. So that's the case of the wind trying to push me back when I'm trying to bike. Okay, so we're going to need to remember that as we work through this. Okay. And if I want to try to figure out the work that's done by this force field, I'm going to go through what should be by now a fairly familiar four-step process. So I'm going to chop. So I'm going to chop this curve up into little pieces. Don't have to make them all the same, but I'm going to. So I'm going to let delta S be the arc length of each of these little pieces. Okay. And if I make it the same, I could just write delta S. If they were different lengths, I'd have delta S with a subscript to indicate that I was talking about the length of the ith piece. Okay. Now I need to approximate the work that's done over each piece. So let's just say that this is the ith piece of curve that we have here. And let's suppose that the vector that we have for the force at this point is here. So I'm going to just choose this as my representative point right here. So I'm just going to call this point pi star. So it's a point, it could be in 2 space or in 3 space, depending on whether our vector field and our curve are in 2 space or 3 space. But I'm choosing a representative point. This then would be the force evaluated at that representative point. Okay. And then this is a curve whose length is delta x. Now, if I want to approximate the work, I'm going to need to sort of approximate the displacement over this curve. So I'm going to do that with a vector, okay, because displacement was a vector when we worked with this before. A vector has magnitude and direction. So for the direction, if I'm trying to approximate the direction of the curve, I think I want to take a vector that's going to be tangent to the curve. Okay, now for a vector that's tangent to the curve, I know that if I've parametrized the curve, r prime, the derivative is tangent to the curve. What I like even better than that is the tangent, the unit tangent vector at that point, because that just has a length of 1, and that means if I scale that by the right value, I can approximate the distance as well. Okay, so what I'm going to do is I'm going to take the unit tangent vector evaluated at pi star. That has the right direction, but it has a length of 1. I wanted to approximate the length of this curve. I'm just going to scale that by a delta S. The unit tangent vector gives me the direction. Scaling by delta S means that I'm approximating the arc length. And then I can say the work over the ith piece is approximately the force at pi star dotted with delta S times the unit tangent vector at pi star. Cool. So now, of course, I'm just going to add these guys and take the limit. So we'll have step 3 we add, and step 4 we take the limit. Now when I do that, I'm going to get that the work is the limit as n goes to infinity. And again, the significance of that is that all of these pieces are getting smaller and smaller and smaller. It's not that we have lots of them, it's that they're all going to 0. Okay. Now, if I've used a regular partition, so they all had the same length, lots of them means that they're all very, very small. But if I used an irregular partition so that pieces were different lengths, I would have to ensure that not just did I have lots of them, but that they were all going to 0. And then it would be the sum, as I goes from 1 to n, of f at pi star dotted with t at pi star times delta s. Now all I did was take that scalar and pull it outside of the dot product. If you remember, we had that property of the dot product, that if I'm dotting a multiple of a vector, I can just take the dot product of the two vectors and then multiply by that scalar at the end, and that's what I've done here. But if I look at this, this is exactly the sort of Riemann sum that leads me to a line integral. So I'm going to be getting the integral along C of f dotted with t ds. Now what I like about this notation is I can sort of see where it's coming from. Work was force dotted with displacement. This right here is my displacement, where t gives me the direction of the displacement vector, and ds is scaling it so that it's going to have the same length as the curve, so that it has the correct magnitude. Okay, so that's how we're going to evaluate, or how we're going to set up some work integrals. This video has been going for a while, so I think I'm going to stop it here. What we'll do in the next video is we'll take a look at an example, and we'll see how we go from here to transitioning to using our parameterization of the curve so that we can switch from integrating with respect to s to integrating with respect to our parameter t. We learned to do that in general for a line integral, but something really cool happens with work integrals. So come back, we'll see.